Let's take a look at the optimization toolbox. This add-on is designed to aid in the estimation of variables and parameters in optimization problems such as regressions. The optimization toolbox has a few functions of its own, but its main feature is a graphical optimization tool, which allows you to optimize a wide variety of equations based on various criteria. This optimization tool effectively encapsulates all of the different optimization functions provided by the toolbox and allows you to specify each of the parameters separately. To access this application, type optim tool in the command window. The tool will then appear in a pop-up window. On the left-hand side, you are asked to specify the solver type, algorithm, objective function, start point, and constraints. The results will then display at the bottom. The right-hand side contains additional options that allow you to specify how the function runs. For instance, if you're running a very slow function, you might change the number of iterations to a lower number so that you get your result quicker. For this example, I'm going to use the optim tool function script, which is provided in exercise files, as the objective function. This is a relatively simple function that calculates a result based on 3 independent variables. Graphing the function to find its minimums would require a 4-dimensional graph, and calculating the derivative to find the minimums analytically would also be quite difficult. But the solver tool can optimize these values easily. In this case, the solver tool is fmin_con because the objective is to minimize the residuals with the variables constrained to certain values. The optimization function is an @ symbol followed by the name of our script, or @optimTool function. Any start point is fine, but for this example, I'll use 1, 1, and 1. The start point can be important if you're dealing with a function with more than one minimum, because the optimization tool can only find a local minimum. It can't guarantee that it will find the absolute minimum. For the linear inequality, the constraint requires that vector A times the input vector be less than or equal to B. So if I put in A is 1, 1, 1, B is 100, that means that X plus Y plus Z is less than 100. Once this is done, click Start to run the optimization. The results are displayed under Final Point, and these values will give the lowest possible function value under the given constraints. Here we have that the first variable x is equal to -0.208, the second variable y is equal to 7.525, and the third variable z is equal to 92.683. All of these variables sum up to just under 100, and they give the lowest possible value of the function given those constraints. The last thing you might want to do is see how the optimization occurred. Under the Options menu, scroll down to the Plot Functions bar and check Function Value, and then run the optimization again. With this selected, MATLAB will display the function value after each iteration, so you can easily see how changing the values caused the function value to drop to its lowest point.